3. So we talk about universal derivations. So let's firstly recall the definitions. So we are following search along algebra. This is page 746. So let A be an R-algebra, let M be an A module, by a derivation from A to M, and over the base ring R is an R linear map. It's not A linear, but R linear map, such that D of AB equals A of DA, A of DB plus B of DA. So quick remark, firstly, so D of 1, so A is our algebra in particular is a ring, so we'll assume this ring have multiplicative identity. So element 1, so in particular this implies D of 1 equals 2, D of 1, this implies D of 1 equals 0, and because this is R linear, and so actually D of R is 0. So definition again. So let's see, second remark. So derivation form an A module is denote derivations over R from A to M. Okay, so you take D from 8, transaction A of D, define out whatever element B is defined to be just A of DB, because this is in M, which is A module. Okay, continue definition. So a universal derivation for A over base ring R is an A module with a derivation. Let's denote this module omega, this derivation small d from A to omega, such that, so the universal, of course there is a universal property, basically any derivation will factor through this. For any derivation, let's use D again from A to M, so M will be some A module again. There is a unique A map, which means A linear map of A modules such that diagram commutes. And then because this is universal property, so which means it is unique. I mean, this universal derivation is unique up to isomorphism. Secondly, by the definition, we have, so this is a module we just defined, all the derivatives from A to M. But whenever you have such a derivation, you got that unique f, and so there is not only a bijection but a factorial isomorphism. Because it's not home, I would not say this is a joint pair, but it's factorial isomorphism. This is not a joint pair, okay? So our exercise today is basically prove the existence of universal derivation. So this will be done in several steps, several small exercises. First exercise. Let F1, F2 be two homomorphism of R-algebras. So A and B are two R-algebra. Let J be an ideal of B such that J squared equals 0. And suppose, assume F1 congruent to F2 mod this idea, which means for any element small a of big A, big ring A, ring big A, sorry, so F small a, F1 A minus F2A is always in this ideal J. Then show that D defined to be F1 minus F2 is a derivation. Okay, this is the first part of the exercise. So, solution. So, let's just check by definition. So D of AB would be by definition F1 AB minus F2 AB, right? But what is this? Let's notice that F2 AB equals, because this is map of R algebras. In particular, this is a ring. In particular, this is a ring homomorphism. And the difference of F1 and F2 is in J. And also, just by definition of big D, I could also just write this, because I mean F2 could be written as F1 plus F1 minus F2. actually f2 minus f1, okay? And then similarly, f2 could be written as f2b could be written as f1b plus d of b. Nothing here. And then notice that d of a is inside J, right? Because by definition, f1 minus f2 is image 4 into J. J squared equals 0, and so when you multiply it, the last term disappears. You have only f1a, f1b plus f1a d of b plus f1b d of a. And the last term vanish, and so this gives you just f1ab, right? So finally you see that dab equals this f1a of db plus f1b of dA. This is not too far from it, but same as not. I claim this is just A acting on dB plus B acting on dA. And so we are done. So why this is it? So actually, this is a question of, so this is in B. This is a question of how is B realized as a module. So same as there are two reasonable ways to do that through f1 or f2, but so they're the same because their difference is in J. And so multiply with dv itself disappears, which means f1a times db equals f2a times db for whatever ab in a, right? So we're done for the first exercise. Let's see the second one. Let's consider this tensor product of R-algebra A. So remark, recall this is an R-algebra, right? So we have multiplication, and we have our linear map, or if you want, there is a ring homomorphism. So this R map is multiplying on the first component or the second, okay? And consider also this. So let me also put this in recall. Recall this is a ring. This is a ring homomorphism, okay? And now, after the recall, denote J to be the kernel of this. And so in particular, this is the idea of this ring. This R-algebra in particular, it is a ring. And definition. We call omega A over R, J quotient by J squared. The module of differential. And so this is an ideal of this ring, right? Remark. Put a module structure. A tensor A by or if you want, you could also still write endomorphism. So tensor A because both are rings, so it's okay just have ring morphism, and then this endomorphism is given by multiplication of this element. Now the exercise is first part. Prove that there is decomposition of A modules. Secondly, J is generated as a module by elements of the form xi dy. So xi yi in A, of course. Okay, firstly, for 2.1, let's say this is just to show this as a module. So you only have to show firstly any element small a tensor B. So notice it is also a B tensor 1 plus some element J. And so let me just say I claim this is in J because by definition J is the kernel of multiplication. A, this is a ring map. So let's just check what it is. This is just by definition. This is ring homomorphism. It's MA of the first term, which gives you AB, minus MA of the second term, which gives you AB. So this is 0. Okay. So we have proved the first A module plus the second A module gives you A tensor A. So secondly, let's check their intersection is trivial. Suppose this gives direct sum. Suppose A tensor 1 is in J, so element is in their intersection, then by definition MA of A tensor 1 is 0. This is just A, so A equals 0, and so this is 0 at the beginning. We proved 2.1, let's prove 2.2. Before we prove 2.2, let's put remark. Firstly, by the decomposition, we have A tensor A quotient G squared equals A tensor 1 plus J, and then quotient J squared. Secondly, let's consider a derivation from A to J quotient G squared, defined by the R linear map. One tensor A minus intersection mod G squared. So actually this is sub-exercise. Or let's put it just third part of our exercise. So D is a derivation. So let's first prove this. So let's say D equals F1 minus F2 with F1 defined to be this, F2 defined to be this. And then notice we are back in the situation of our exercise 1. Because notice F1 congruent to F2 modulo J. Because their image always in, sorry, let's say yeah, trivially this is true, and also G squared equals 0 is true, right? So this is directly a derivation. Now let's back to exercise 2.2. Show that this J is generated by that elements. So suppose we have element in this ring that is in its ideal J. Then by definition, what is J? J the kernel, right? The kernel of this MA. And it should be give you the summation. this xi minus yi in A. Hence, we can rewrite our expression xi tensor yi into xi tensor 1 tensor yi minus yi tensor 1. Why we can do this? Because it's not a tensor multiplication, so this is in A. So this gives you a module structure. This is a tensor A. A tensor A is defined to have a module structure through the multiplication of the first variable. So this is also proved this is true because when you multiply, this gives you this. This is the first term. The second term gives you, right? But this is 0 by our computation or definition of J. And so this gives you back here. Okay, but now what's new here? This is also of the form. Notice this is just our d of yi. So finally this equals xi times dyi. So the claimed structure, the claimed form. So exercise 4. This is a theorem. In Search Long's book, this is theorem 3.1. The pair J quotient J square D is universal for derivation of A. So actually we have, this is finishing the goal, which is to prove the existence. So we have to give a construction proof. I have proved this universal derivation. So in our notation, this is called omega AR, right? We define this to be omega AR by our definition. So let's recall this means that we have this is J over J derivation. I have proved this is derivation firstly, and secondly, what we are left to do is that for any derivation there exists a unique derivation. There is a unique ring of homomorphism. Sorry, there is a unique morphism of A modules such that it commutes, right? This is what we have to prove. Proof. So this is an ideal or submodule of this ring, right? So let's first construct. Construct a bilinear map and hence gives to the unique map of A modules from the tensor product of A with A to M. And so how is this bilinear map is defined to be mapping xy to x dy. And so it's a small exercise, sub-exercise to check this is indeed bilinear. actually there's no difficult. Let's quickly check it here. So the difficult part is for, of course I have to mention this is R bilinear. Both AI are algebras. Because this is, let's call this F. By definition, this is x d of ry, and so this is x r dy, y dr. Right, but dr is 0, so this is only one left, but this is also r of x dy. The reason is that by definition R-algebra, so the image of R is actually in the center of A, right? And so this gives a universal property of tensor product, a unique R-linear map. Such that x tensor y is mapped to x dy. Well, this is also a map of R modules, right? R bilinear map between R modules. And so this is a unique R linear map of R modules, if you want. Yes. Notice this is also a linear, because by our definition the first part is a module by multiplication of the first factor, right? And so this is the map of x dy, which equals, let's call this f tilde, which equals, so af x tensor y equals f of, sorry, this is actually f of a x tensor y equals a of x tensor y, right? And so this is a linear. And then you notice that what have we done? We have constructed a linear map, right? We constructed a linear map. Not only on J, but on a tensor A. Notice so, I mean, we've constructed one, and the unicity, let's say you have to basically have to construct one and show the existence, and then you show the unicity. Right. What we have done is that we have constructed one, right? The diagram is commutative over A because A is mapped to, let's say, D of A, which is by definition 1 tensor A minus A tensor 1, and this by our constructed map is mapped to 1dA minus AD1. AD1 is 0, so this is just dA, and so this is mapped to dA. This is commutative. We have constructed one, so we have to show the existence. But this doesn't show the unicity, right? Actually, basically, the way you define it in this way is just your way to construct the unicity. The unicity here, I mean the unicity are linear map such that it's mapped to this. This doesn't tell you that the unicity of F tilde, right? Because this is not. And how do you show the unicity? Notice that, or recall that J is generated by elements of the form x dy with x in A, right? So this is already dy. So dy is mapped. So dy is, the image of dy is unique, but this is alinear. So F tilde is unique over the generators of J over J squared, so it's unique over J over J squared. So finally, summarize what we have proved is derivation over R from R-algebra A to A module N is isomorphic to the A linear maps as a module from the differential of A over R to N. This is very similar. This is very similar as disjoint pair, but it's not.